All right, so we're going to talk about acceleration a little bit more. So we've already determined that acceleration is a vector. That's from our original list from the beginning of the year. And we figured out a definition of acceleration, the rate of change of velocity. Remember, we had talked about the notion that initially we said the rate of change of speed. In fact, the initial thing we said was the rate of increase in speed, because that's the way that most people conceive of the concept of acceleration. So I'm going to just write that down, that most people's preconception of the idea of acceleration, what gets in the way of us understanding the concept is we think it's the rate of increase in speed. And so two things wrong with that. One, speed versus velocity. And then we realized that if acceleration is a vector, it needs to be dependent upon other vector quantities. So that makes sense that we changed that from speed to velocity. And then the next thing was we went from increase to change because we wanted to broaden the concept of acceleration, because we figured out that it made no sense that if I push and pull an object, that different quantities would happen based on what was going on. Didn't make sense that slowing down because of a push and speeding up because of push, that there was no real big distinction between those, and therefore we had this unity of concept that we want to generally just change rather than increase. So what does that mean then? That means that there are three things that we could be looking at and see that acceleration is occurring. The first is that the speed can change, and that change in speed could be either speeding up, the way we traditionally think about acceleration, or slowing down, and that is acceleration. And then the other thing we could say is that there's a change in direction. And remember what we mean by change in direction. That means traveling in a curved or nonlinear path. And so hopefully by the end of this, we will understand a little bit more about when things speed up versus when things slow down versus when things change direction because they're accelerating. Okay, before we get too far, um, I wanna do some grammar with us here. So words that we're going to use when we're talking about things like velocity. So verbs that we're going to use when we're talking about velocity are going to be things like go or move. So an object is moving at a velocity of 4 meters per second. An object is going at a velocity of 4 meters per second east or whatnot. Um, it's important we use those words. As opposed to acceleration, I don't want to use the word go with acceleration, because acceleration isn't about the way things are moving. It's about how the way we're moving is changing. So we want to have a different verb that goes with that. And we figured out that forces, pushes and pulls, are what cause things to change the way that they're moving. Just a quick demo in class, we showed that, which is why when we're talking about the word acceleration, we want to talk about the acceleration acting in a certain place, as opposed to position. That's just where things are, right? And so different verbs are connected to different ideas, and that language is really important as we're being consistent as we go through. Okay, great. So next, let's talk about quantifying this. So acceleration. If it is the rate of change of velocity, we could probably presume what the equation is. So we were looking at velocity as being the rate of change of position, and we wrote the equation for average velocity down. I'll put this off to the side. I had the change in position through time, right? Or delta S over t. Well, now that I'm talking about acceleration, this is the rate of change of velocity. So hopefully you can see that a similar type of equation is going to evolve. Since it's a rate, we're going to have definitely a ratio here, and then the denominator of that ratio is going to be time. And I'm going to put some vector symbols on that to make that good. So there we go. That's going to be our acceleration equation. Now I can write that in a different way because I can expand what delta means. Delta means change, yes. But if you think about like in the slope of formula, when people say delta y over delta x, they say y2 minus y1 over x2 minus x1. In physics, don't want to talk about twos and ones. Instead, we're talking about how things change through time when we're talking about rates. So we don't want to talk about one and two. We want to talk about an initial situation and a final situation. And a delta always expands into final minus initial. So that says the final velocity minus the initial velocity divided by the time is equal to the acceleration. So that's an expansion of this. So these are the same equation. But I want to define my terms a little bit more. So VF, or VI, excuse me, this is going to be the initial velocity in the interval. Okay, that's an important phrasing. The F is the final velocity in the interval. Because you might ask, why isn't this t in here a delta t? Well, technically it is. We're just not going to write it. And here's why. When I say the initial velocity in the interval, that doesn't mean like the initial velocity of the object, like since it came into being. It means the initial velocity of the object when I started caring about it, which means that, like we have seen in other problems, like when we did the truck lab and we played with the trucks and we put it down and we started the stopwatch at a very particular point as it started the start line, it had a velocity before we cared about it, but we had the power of the stopwatch, so we were able to say t is equal to 0 at the beginning of the interval that we cared about it. So I'm going to write that down as the power of the stopwatch is really important because that lets us decide when t equals 0 occurs, i.e., when we begin to care. And probably it's a little emotional there, but that's that. But then why does that solve our conundrum here? Well, because delta t, folks, would be t final minus t initial. And if I just set the initial time to when I start caring about it to be 0, then delta t is the same thing as t final. And so therefore, we can just conceive of t then, therefore, as the time length of the interval. Okay? So in other words, t is the length of time that the interval goes on. The I is the velocity at the beginning of that interval time. The F is the velocity at the end of that interval time. Great. So we have our acceleration equation. Now, coming up to the top again, anytime we have a new quantity, we want to know if it's a vector or a scalar. Check, done that. We also want to know its units. So I can come back here and say A brackets, right? Question mark, right? What are the units of A? So the units of A are going to be the units of the change in velocity divided by the units of time. And therefore I get meters per second divided by seconds, which is a really odd thing, but actually that's very meaningful because if I complete the complex fraction, meters per second squared is the like shorthand way of writing it, but that doesn't make any sense, right? Seconds squared, like lots of time. I mean, what is that, like some sort of area of time? Like, what does that even mean? It makes no sense. But this meters per second is going to be quite meaningful for us because the way I want you to think about this is not meters per second, but meters per second each second. Okay? So anytime we see meters per second squared, we're going to say meters per second each second because that's going to reveal the meaning of what acceleration is about. So coming over here, let's say something has an acceleration of 4 meters per second each second to the right. What does that mean? Okay, so stop the video, see if you can think about what that means. All right. Well, a common thing that people think this means is the velocity increases by 4 meters per second each second. And to us, we would say, uh-oh, that is a problem. But that's the way that people want to think about it. Once again, that encodes the preconception that acceleration is all about increases in speed. So, what is really true about that? Well, first off, this right, we can't deal with this right here, but we're eventually going to turn that into some signs. But what this is saying is, so this is wrong. What is correct is to say is the velocity changes by 4 meters per second right each second, right? But what does even that mean? Well, we're going to see it in practice and it'll make a lot more sense. Okay. But that's the way we want to decode what that statement means. So we're going to do a series of examples in order to highlight what we're talking about. All right. And what to do with examples, we're going to look at some graphs. Here we go. So I've got this packet and I'm doing, if you notice, I have a little chart here, and some graph paper here for some sketches. So let's say something has an initial velocity of 0 meters per second, and I'm going to use my 4 meters per second to the right? So the acceleration is equal to 4 meters per second squared to the right. And I'm not going to deal with that because I know it's a vector quantity. I've got to make a declaration. Let's say right is positive for this. Okay, so that means that this acceleration is positive 4 meters per second each second to the right. All right, so time equals 0. I have my velocity, and that's equals 0 because I defined the initial velocity to be 0. So then after 1 second, what does that mean? Well, if my velocity was 0 meters per second at the beginning of the first interval, and the velocity is going to change by 4 meters per second to the right each second, after 1 second, I'm traveling 4 meters per second to the right. After 2 seconds, I have a velocity of 4 meters per second to the right, and I add to that another 4 meters per second to the right, I end up with 8 meters per second to the right. So the plus meaning the right here. So plus 12, plus 16, plus 20. Hopefully that sequence makes sense. A couple of things about that. What's the motion? Hopefully you would say that this object is speeding up. And you'd be correct in this case. And you might be saying, hold on a second, Juan, I thought you said that acceleration doesn't mean speeding up. And what I said is acceleration doesn't necessarily mean speeding up. In this instance, it does. So we're going to have to figure out like why in this instance does that mean it? But anyway, from the data, what is our evidence that this is speeding up? So our evidence from our data is that the magnitudes of the instantaneous velocities are getting higher. I'm going from 4 to 8 to 12 to 16 to 20. So it's important to say not that the velocity is increasing, but the magnitudes of the instantaneous velocities are increasing. So here we go. The magnitudes of the instantaneous velocities are increasing. Awesome. So we've got that. So let's take this and let's plot ourselves a graph. 1, 2, 3, 4, 5. And we're going to make ourselves a what's called velocity versus time graph. So plus 4, plus 8, plus 12, plus 16, plus 20. And this is V versus T. And if I were to plot that, I'm not circling my points because these are mathematically generated points. This is not an experiment that I'm doing. Boom, 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 boom. And then hopefully what you can see fairly clearly is I get a trend like that. Awesome. So what we're going to do is talk about some graph facts about the velocity versus time graph. I'm going to do them all on a separate sheet of paper so I can have one list of them. So here we go. Graph facts. Velocity versus time, because we have graph facts about our other position, distance, and displacement versus time. So here we go. What's the first question I'm going to ask? And that's 0, 0. Now, in this case, 0, 0 is a point on this graph. But my question is not, is it a point on the graph? Is, must it be a point on the graph? So stop the video, ask yourself that question. So when you come back, 0, 0, nope. This does not need to be a point on the graph. Well, why not? Well, because we have the power of the stopwatch. I can start the clock when I start caring about it, like we did in the truck lab. That object was already moving when I started caring about it. In this example, I told you the initial velocity was 0, but that doesn't necessarily have to be true. So this does not need to be a point in the graph because if VI is any other number than 0, 0, 0 will not be a point on the graph. Okay? Therefore, what is the vertical intercept? When time is equal to 0, the vertical intercept is the initial velocity. So there's our first graph fact. Cool. So then the second question I always ask, what's the value of that slope? Stop the video, find the slope. Okay, and you're back. Hopefully you found out that the slope of that line is 4 meters per second each second. So there you go. The slope of the velocity versus time graph is the acceleration. All right, awesome. So now going back to the graph, we know the value of the slope. What else is true about this slope? And you should be able to make two observations about this slope. One, the trend is linear. Therefore, the slope is constant. Okay? So what does that mean that the trend is linear, that the slope is constant? Well, if the slope of the velocity versus time graph is the acceleration, that means a linear graph means constant acceleration. All right. So kind of what's the side thing about that? Well, if linear graph means constant acceleration, what would a non-constant acceleration look like? And that, of course, is a curved graph. Means non-constant acceleration. All right, awesome. So coming back to this now, we know that that graph is linear, therefore the acceleration is constant. What else could I say about that graph? And hopefully what you say is, oh, the slope is positive as well, right? It's like this, not like that. Okay, so what does the fact that the slope is positive mean? And it's very tempting, but very wrong to say that this object is speeding up. So I'm going to write that as a note. The positive slope does not mean necessarily speeding up. And I know that's weird. I know that's very weird, but I want you to hold on to me. Hold on with me. Ready? Let's go back to this. The slope of the velocity versus time graph is the acceleration. The slope is positive. That means the acceleration is positive. What does that mean? And people still want to say positive acceleration means speeding up. That's not true. Positive slope does not mean speeding up. Positive acceleration does not mean speeding up. Okay? So what the hell does it mean then? Well, the positive sign on acceleration goes back to the fact that acceleration is a vector concept. The positive sign here just merely means to the right. And so the sign of the slope just tells you the direction of the acceleration. Okay, right? So the sign of the slope just tells you the direction of the acceleration. All right, great. So I'm going to go a little bit away from graph facts. We're going to come back to that for a second because we just brought up the phrase constant acceleration. What does that mean for an acceleration to be constant? Well, if we remember that acceleration is the rate at which velocity changes, this says the change in velocity each interval is the same. That's what it means. Now, I want to contrast that to constant velocity. What does constant velocity mean? Well, constant velocity meant two things to us. One, it meant the change in position or displacement. And by the way, change in position is displacement. So I'm not saying the change in position or the change in displacement. I'm saying the change in position or the displacement each interval is the same. Okay, that's what we said about constant velocity. Or we said at every moment, the instantaneous velocity was equal to the average velocity. Okay. And that's what it meant to go at a constant velocity. So the change in the change of position in each interval is the same. Okay, well, that's going to help us figure out some things about what it means to speed up or slow down. Because if I'm traveling at a constant velocity, I'm traveling at equal distances or displacements in equal units of time. If I'm speeding up, that means in first interval, I'm going so fast. In the next interval, I'm going a little bit faster. In the next interval, I'm going even faster, and so on and so forth. So what must happen to how far I'm traveling? So hopefully what you realize is that when I'm speeding up, an object will travel larger distances in each successive, meaning next, time intervals. And that's actually what we see when we watch something speed up. You may look at something speeding up and say, like, oh, I see it going slower and I see it going faster. You can't actually observe speed. What you are actually observing is a certain distance covered in time, and then your brain is extrapolating that into saying something about the speeds. And then for acceleration, it's saying, oh, I saw this distance covered in this time here and this distance covered in this time here, those were not the same. Therefore, the speed changed. Therefore, it accelerated or it sped up or it slowed down. So the brain is doing a lot of mental gymnastics that we have to really understand that all we can ever observe is distances in certain amounts of time or displacements in a certain amount of time. Similarly, for something that's slowing down, what's true there is an object will travel smaller distances in each successive time interval. Okay, so there we go. So we have a very clear difference here between something that's traveling at a constant velocity and something that is accelerating, and specifically at a constant acceleration, right? So this is kind of going back to why I said I never want to hear the phrase the motion is constant, because what's constant is what's constant the acceleration, the velocity, the position, the amount the position is changing by, the amount the velocity is changing by. It doesn't mean anything. All right. So going back to this graph, this object we see over time is traveling to the right. But what about the graph? So all these values are positive. So what about the graph? What observation can we make about the graph that will tell us this object is going to the right or going forward? Well, if all the values of the velocities are positive, I would expect the entire trend then is in that first quadrant, right? And so we get another way of reading the velocity versus time graph, graph X6, objects moving whatever the forward or positive direction. So moving, meaning with velocities that are positive, will have a trend in the, I don't even want to say in the first quadrant. We'll describe it a different way. Here is the time axis. Where is the trend? That trend is above the time axis. Okay. And therefore, an object moving backwards, which we just said like is generally negative, will have a trend below the time axis. Okay. So there's one last thing for now that we want to say about velocity time graphs, and it is what about the graph observationally tells us I'm speeding up? And it's very, 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 very tempting to want to say that it's that positive slope, but I'm just going to come back to positive slope doesn't mean speeding up. So we're going to do a whole bunch of other examples. We're going to figure out when an object speeds up and when it doesn't. So here we go. We'll do a whole bunch of graphs now. So let's say our initial velocity is positive 6 meters per second. So 6 meters per second to the right. So I start the stopwatch as this object passes me. And it's already going 6 meters per second to the right. But let's say its acceleration is 0 meters per second per second. So stop the video, see if you can do the chart and the graph. Okay, if you're back with me, hopefully you realize that all of these velocities are positive 6, right? Because the zero acceleration says there's no change in the velocity. This is what the velocity is at t equals 0. So if I were to say, here's a graph with 2, positive 4, positive 6, positive 8, positive 10, that's my velocity, meters per second. T in seconds, 1, 2, 3, 4, 5. That this graph, grab my straight edge, is just going to look like that. So let's see if this verifies our graph facts. So think about what that says. So if you want to stop the video and write a couple things down, try. Great. The fact that that graph entirely is above the time axis tells it is indeed going forward or to the right. The fact that it's not that does not have an intercept at 0, 0 means that it's moving initially, right? And that initial velocity, that vertical intercept is plus 6 meters per second. Great. The fact that its acceleration is 0 because the slope is 0. Fantastic. So um, this really does correlate with a lot of our graph facts. All right, cool. Let's do a couple more. Hopefully we start to see some trends. So let's say that our initial velocity now is positive 10 meters per second, and I'm accelerating still at positive 4 meters per second each second. So I'm going 10 meters per second to the right initially, and I am accelerating at 4 meters per second each second to the right as well. Okay, stop the video, make your chart, make your graph. Okay, if you're back, you should have plus 10, plus 14, plus 18, plus 22, plus 26, plus 30. Okay, I'll come over here and quickly sketch that graph. I'm trying to remain um, consistent with doing all the nice things with graphing, even though I'm trying to go fast, right? We don't want to miss things. So rather than plot each point, I'll just kind of plot the end lines here to make that go a little bit quicker. All right. All right. Does this gel with what we thought? Once again, it's going to the right. Trend is above the time axis. It does not beginning from at rest. So therefore 0, 0 is not a point. Still, I have this nagging bit. Well, first off, is this object speeding up or slowing down? Hopefully you look at the data and say the magnitudes of the velocities are increasing, therefore it's speeding up. And it's still this like pesky um, bit where, it's a positive slope, but it's speeding up. All right, we got to do some more in order to figure it out. All right, let's say my initial velocity is positive 20 meters per second, but my acceleration is negative 4 meters per second each second. Okay, what does that mean? That means I'm going right initially, but the acceleration is acting left at 4 meters per second each second. Right? 1, 2, 3, 4, 5, t in seconds, v meters per second. We'll use plus 4, plus 8, plus 12, plus 16, plus 20. There we go. Negative 4, negative 8, negative 12, negative 16, negative 20. Stop the video. See if you can figure this out. Great. Hopefully what you got, plus 20, plus 16, plus 12, plus 8, plus 4, and 0. And if I were to graph that, okay, there you go. Is this object speeding up or slowing down? Look at the data. Hopefully you said it is slowing down. And what is our evidence of that? Our evidence is the magnitude of the velocity or the instantaneous velocities, excuse me, is getting smaller. You can't see that on the screen. Let me move that up. The magnitude of the instantaneous velocity is getting smaller. All right. But this seems to be falling into that trap because we said that, you know, positive slope wasn't necessarily speeding up, but now I have a negative slope to the acceleration and it's slowing down. It seems to be building an opposite case of what I keep trying to tell you to watch out for. But let's just make sure this negative slope, what that means once again is that I'm accelerating to the left. The sign of the slope is the sign of the acceleration. Okay, so all that gels. I'm moving forward still, right? This thing is moving to the right, getting slower as it's moving to the right, but it is moving to the right, which is why the entire trend is above the time axis. Okay, here we go. Hopefully one last example here, and this is the one that starts to bring it together. Let's say our initial velocity is, oh, I don't know, negative 4 meters per second, or sorry, negative 4 meters per second. And our acceleration is also negative 4, but meters per second each second. So initially, I'm moving to the left, but my acceleration is acting at 4 meters per second to the left. Stop the video, make the chart, make the graph. Okay, hopefully what you got, negative 4 meters per second, negative 8 meters per second, negative 12 meters per second, negative 16 meters per second. I don't know why I'm drawing the meters per second, but I'm doing it, so I'm just going to keep going. Great. And then coming over here to the graph, we do have to extend this just a little bit. I got 1, 2, 3, 4, 5, time in seconds, velocity in meters per second, negative 4, negative 8, negative 12, negative 16, negative 20, negative 24. Great. Plotting the points, boom and boom. I could plot all of the points as I go along, right? If I want to be really particular about it, but this will get the job done. And so there we go. Well, sorry, it's not wonderful, but there it is. And now we start seeing something. All right, so if I look at this, is this object speeding up or slowing down? And this is a tricky thing because you might say these numbers are getting smaller because the numbers are trending towards negative infinity. But that's not the way to think about it. Is this thing speeding up or slowing down? Well, it's speeding up because the magnitudes of the instantaneous velocities are getting larger. But if you notice here, the magnitude of the instantaneous velocities are getting larger, but I got a negative slope. Therefore, negative slopes don't mean slowing down. Positive slopes don't mean speeding up because I've got a counterexample. Okay. So then what is it about this graph that means I'm speeding up or slowing down? And if you look back through the trends, let's take a look. That's speeding up and that's speeding up. This object is neither speeding up or slowing down, and that's slowing down. Hopefully, what you can see as a trend is what the way to observe on a velocity versus time graph, whether or not the trend says speeding up or slowing down, it's the relationship of the trend to the time axis. In the situations where the trends were doing this, moving away from the time axis, or more properly, if the trend diverges from the time axis, that means speeding up. Because then the trend is moving towards larger negative or larger positive numbers. And if the trend converges on the time axis, we're slowing down. All right. So that helps us out with all of that. So far, so good. Okay. Last bit on all this. I really want to get into when do things speed up or slow down. Okay. Because so if positive acceleration doesn't mean speeding up and negative acceleration doesn't mean slowing down, we saw things with the positive acceleration that caused it to speed up. We saw something with a negative acceleration that caused it to slow down. And we saw something with a negative acceleration that caused something to speed up. So stop the video and see if you can figure it out. Hopefully what you figured it out was when the acceleration and the velocity had the same sign, I was speeding up. But it's not enough to say same sign, because if I have two axes, I could have two positives, but they don't mean the same thing. Here, when I say same sign, I mean same direction. So if the velocity vector and the acceleration vector are in the same direction, and the proper way of saying that is are parallel. The object speeds up. And that should make sense. If I'm going to the right and I want to speed something up, I push it to the right. If I'm going north and I want it to go faster north, I push it north. As long as you push something in the direction that it's going, it will speed up. Therefore, slowing down if the velocity vector and the acceleration vector are anti-parallel, meaning the opposite direction, not different, opposite direction, the object slows down. And that should make sense. If I'm going to the right and something pushes me left, I'm going to slow down while moving to the right. If I'm trying to go north and you pull me south, I'm going to slow down as I'm moving north. Now, interestingly enough, if I'm going north and you pull me south, I'll be slowing down while going to the north. If you pull me long enough, I'll actually start speeding up while going south, which is very interesting. And we'll talk about that another day. But we said that there are three things that could happen with acceleration. You can speed up, you can slow down, or you can change direction. Well, when do I change direction? Well, here, if the vectors are parallel, I speed up. If the vectors are anti-parallel, so let me just draw this. So there's V and A drawn concurrently. Here's V and A draw concurrently, but in opposite directions. When do you think I change direction? Well, hopefully you figured out I change direction if V, or how about this? Change direction without changing speed when V is perpendicular to A. Because that's the only other option we can have. Parallel, anti-parallel, perpendicular. And if you think about that, if you throw a piece of chalk to the right in the air, gravity is pulling down, and you can see that it goes in a curved path. Because remember, when we say change direction, we mean curved path. And if you really understand the concept, you can get this, which is how we ended class. If I am moving to the right and my acceleration acts like this at some weird angle, what's this doing? Hopefully you figured out this object is both speeding up and moving in a curved path. And why is that? Because there's a component of the acceleration that's along the velocity, and there's a component of the acceleration that is perpendicular to the velocity, right? So kind of bringing back together all of those notions that we talked about acceleration. So this is the foundational aspect with acceleration. What we have to talk now about is equation work as well as how far do things move while they're accelerating. But this gets us through our acceleration ideas. So with that, there we go.